Welcome back to Calculus AB. Today we're going to start Unit 3, differentiation of composite, implicit, and inverse functions. So pretty much today's objective is going to be that you're going to calculate derivatives of, compositions of differentiable functions. And the main topic today is what we call the chain rule. All right. So first, let's introduce this new differentiation technique by showing you the types of functions that would require its use. The table below illustrates pairs of similar functions that can be differentiated with and without the chain rule. So pretty much you guys see we've learned different techniques, right? So we've learned already the power rule, the sum and difference rule, right? We know what happens if we have a constant in front. We can just put it to the front and so forth, right? Those things still apply here. So we're adding to what we learned. And again, the chain rule is another technique that makes it a lot simpler for us to actually take derivatives, right? So again, we're looking for techniques, right, for different ways for us to be able to get to a differentiated function as quickly as possible, right? Especially because when we're taking the test, you want to do it quick, right? So here you have different types of functions that require the use of the chain rule and ones that don't require the use of the chain rule. And if you guys pretty much can tell some of the differences right here, right? The first one that says that we can't use, that we don't need to, right, is y equals x squared plus 1. Again, here obviously you would use pretty much just the power rule and the constants and you're done, right? For the next one, again, you have the sine of x. For that one is just the derivative of that would be just cosine of x, so no use of the chain rule, right? Y equals 3 of x plus 2, same as the first one, right? Same rule. And then y equals x plus tan of x, so pretty much the same combination of both the sum and difference rule, the power rule, and of course the trig rules, right? So now look at what's different here. So if we look at the chain rule, so we have y equals the square roots of x squared plus 1. On the next one, we have y equals sine of 6x, right? Y equals 3x, and then that raised to the fifth power. 3x plus 2 raised to the fifth power. And then lastly, we have x plus the tangent of x squared. So what do you guys notice here? What are the differences between both the ones that you need and don't need the use of the chain rule? What do you notice? So pretty much where you need it is where you use what we call composite functions, right? Is when you have a function inside another function. So let's look at pretty much how we're going to deal with this. So if y equals f of u is a differentiable function of u, and u is equal to g of x, another function, right, is a differentiable function of x, then y equals f of g of x is a differentiable function of x. And the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. So we're going to connect these, right? We're going to see, or equivalently, the derivative of f of g of x with respect to x is equal to f prime of g of x times g prime of x. So here again, pretty much what you guys want to do is, if you notice, the rule is pretty simple, right? It's the derivative of the outside function and then times with the derivative, so the derivative of the outside function with the inside intact times the derivative of the inside, which is this part, right? So again, let me say it one more time. So the derivative of the outside function, which is f, right? That's where you get the f prime, with the inside intact, right? You don't do anything to it, times the derivative of the inside function, which is g of x, right? So an easy way to remember here is, again, you're working with layers, right? It's like in that Shrek movie, pretty much. You have layers, right? Like an onion, you're peeling off those layers. So another way to look at it here would be, think of the inner function u of g of x, where u of g of x as being the bubblegum center of Charms Blow Pop, and then the outer function y equals f of u is as being the candy shell, right? There's an extra f of u in there. So let's look at example 1 right here. Let's try to identify which ones are which. So y equals f of g of x, right? So we're looking for the internal function and the external function f, right? So f is the out function, g is the in function. So rewrite using parentheses. So again, first thing we want to do is set this equal to. So you want to make sure that if you see anything that's a fraction like this one, you want to rewrite it with a negative exponent. So x plus 1 raised to the negative 1. And then here you want to identify the bubble gum, right? The internal function. What is the inside one? Which in this case is u or g of x. So we can say u is equal to x plus 1. And then the outer function, which is our y equals f of u, right? So pretty much our outer function, if you were to cover this up, right? The outer function is just u to the negative 1. So u to the negative 1. This is still x plus 1. All right. So let's try it again now with b. You have y equals sine of 2x is equal to sine of. So again, rewrite it with parentheses so you can identify the internal and the external. So sine of 2x, right? So my internal function in this case would be u equals 2x. And then your external function y would be equal to sine of u. All right. So again, we're breaking down the problems into simpler steps, right? And then again, we still haven't taken the derivative yet. We're just learning how to break it down, right? So identify what's the outer, what's the inner function. So again, let's rewrite the next one. We have c is y equals the square root of 3x squared minus x plus 1. So the first thing you want to do is rewrite it with parentheses, right? And again, it's a square root, so make sure you're rewriting it with in fractional exponent. So this is equal to 3x squared minus x plus 1 raised to the 1/2. And now we want to identify our u, right? Our internal function. In this case, it happens to be 3x squared minus x plus 1. And then our external function would be y equals u raised to the 1/2. So that becomes a lot simpler for us to actually be able to solve it, all right? And then the last part right there, example 1D. So again, rewrite it with parentheses so you can identify the external, the internal function, right? And then work your way from there. So our first step is still the same thing. So this is going to be equal to, we have a squared. So remember, whenever you have a square there, you're going to rewrite it as tan of x and then quantity squared. All right. Our internal function will be u equals tangent of x, and then our external function, the ones that's dependent on u now, would be y equals u squared. So in example 2, find the derivative of y with respect to x, and then we have the equation y equals x squared plus 1 raised to the third power. So again, we want to break it down, right? What's our internal function? What's our external function? So first, let's find u, right? U is our internal function. So that's pretty much going to be just x squared plus 1, x squared plus 1. And then y would be our external function. With respect to u would be just u to the third power, right? So now when we want to find dy dx, so dy dx, that's going to be equal to, so again, it's the derivative of y with respect to x times the derivative of u with respect, derivative of y with respect to u, and then times the derivative of u with respect to x. So first, we want to find the derivative of y with respect to u. So that would be just pretty much finding y prime here, right? And that's just going to be 3u squared. So 3u squared replaces the first part. And then u prime would give me the derivative of x squared plus 1, so that'll be just 2x. So over here, we're going to put times 2x. And then we would just want to simplify, so we want to resubstitute what u represents. And again, that's x squared plus 1. So that gives us 3 times x squared plus 1 times 2x. And then you just want to simplify one more time. So that's going to give us 3 times 2x is 6x. So our derivative is 6x times x squared plus 1.